Hi, this is Mohammad Sadiq Rahman. So, as part of the requirement of the AI course, I'm just going to record the assignment 9 video of an understanding. This assignment is about proximal policy optimization, PPO in short form. So, it is a method that provides better stability than other reinforcement learning, and it just updates the policy network to maintain fixed ratio of the old policy and the new policy. But it doesn't abruptly update the policy randomly. So it just update the policy on some robust hyperparameter tuning. So it makes a very good choice for reinforcement learning because it prevents drastic changes of and and provides smoother updates to policy. So here we are going to discuss the very popular artery game Pong. So here this is we are seeing that this is the left side. This is the red agent is not performing well because it is an untrained agent. Now with the proximal policy optimization, we'll train the agent so that it can perform well, and we'll see how the performance is being better and better after the agent being trained with that policy. So for that, we are just referring some built-in functions from Torch and Gymnasium as gym for creating the environment. And here at first we're just importing the game from Gymnasium library and save it to the environment. And if we print the environment, we can see that there are total stages observation is 200 train 160 by 3, that is 210 by 160 pixel, as it is a colorful image. That's why it has 3 channels. That is for RGB channel, and it has in total 6 discrete actions. If we want to see what are the actions, we can find the action is from the value ranging from 0 to 5. That is 0 means no, then a fire, then a right move, left move, and right fire, left fire, and so on. So in here there are six means different actions. So these are that level actions. So at first, for better computational speed, we just convert these 210 to 160 pixel to 80 to 80 pixel, and we convert the RGB channel to single channel grayscale. And for this, we are just converting this. And after converting, before pre-processing, that was 2210, that is 210 in the y-axis and 160 pixel, and it was colorful RGB color. That's a 3 channel. After some pre-processing, just executing this code, we got 80 by 80. That's 80 by 80, and it's only single channel. So one is just omitted here. So here you can see that is the color are vanished. So everything is coming from grayscale with lower dimensions, 80 by 80 pixel. So now we'll define our policy at first initialization, and we are just doing with putting some multi-layer description here. It is we are putting some conversion to the convolutional layers, that is input channel 2, output channel 4, for kernel size 6, that is stride 2. And the next convolutional layer, we just keep these output 4 layers coming the input as 4, and it produces 16 output layers, so with some kernel size. And finally, the total for a fully connected layer, the total output is 256 neurons, and finally these 256 come in the second layer of fully connected layer, and finally this is only one output because we'll just pass the output through a sigmoid function that will only provide for binary classification 0 and 1. That's why we are just using this 1 as the output variable, and we are just applying ReLU activation functions here. So this was all the policy architecture of this agent. And for hyperparameter, we're just setting learning rate at 1 to the power -4, and we're just dealing with the 2 actions, that is left move and right move. And we're using Adam optimizer from Keras. So for calculating the loss function, we're using clip surrogate loss function. This has actually 2 parameters, and it calculates the expected value of this minimum of these 2 parameters. Here there are some terms, that is RT theta, This is nothing but the ratio of the old policy and new policy. Is the ratio that is at a certain state and action. What was the old policy probability? What is the new policy probability? This is defined as the ratio. And there is another term that is A. The A is nothing but the quality value from a certain state action pair, and it's a difference from the state value function. This is AS, and it is also called advantage function. And here the hat means you are calculating the estimation value. The second term, if you see, is the clean version of this ratio 1 minus epsilon, 1 plus epsilon. This is the epsilon is the hyperparameter. So if the epsilon has a lower value, that means we don't want to change this ratio in a very large variance. And if epsilon has a higher value, that means we are allowing very high variance. So we're calculating the mean value of these two, and this expected value will just define as surrogate loss function. This is all about the description of this equation, and all the parameters are defined here. That is a ratio, advantage function, second term, epsilon, and this function, everything. And after the calculation of advantage function, here is another term, entropy regulation term will come here in code. We'll just describe it later. So for calculating the surrogate loss, here is some parameter that is the policy, that is the current policy, and old probability, that is the probability from the old policy, current action stage, and also reared and discounted factor is sitting as 0.995. This is the epsilon 0.1. It means we are not allowing the policy to be updated by a very high variance. It should be from -1 minus epsilon, 1 plus epsilon. That is it will vary from 0.9 to 1.1, and the beta hyperparameter by 0.01. So here we are first calculating the discounted rewards. That's multiplying the discounted factor with the reward, and we're just converting this reward for future reward, and we're just normalizing the rewards by this reward minus mean of the rewards by standard deviation. That's why we're just calculating the mean by standard deviation, and the formula is just like that. That is future reward minus mean by standard deviation. By here, we just got our normalized rewards. Now we're just getting our old probabilities and new probabilities to find the ratio. It is the old probabilities from old actions, and the new probability from current policy and current states. And if when we get this new probability and old probability, if just take the ratio, we just got the ratio, that is RT theta, this term. And for calculating the next term, there was a ratio, and that was within this range 1 minus epsilon, 1 plus epsilon. Here we define epsilon as 0.1, so it is 0.9 to 1.1. Within this range, we have to we'll allow the policy to change the ratio, and we'll find the mean values of these ratio times rewards, was nothing but the AT theta, that was the approximation of the advantage function. And same for creeping to reverse. We can see that here this AT is common in the both sides. So at first we calculated RT theta, then we calculated creep version of this, then we multiplying this. So we get the two values, and we're calculating the mean value and this expected value as the surrogate loss function. And entropy is required for regularization term that comes from this formula, and we're just returning this surrogate function, loss function. So hyperparameter, that is the episode will allow for 250, discount rate at 0.99, epsilon value 0.2, beta 0.01, and the number of maximum steps in each episode is 320. And the epoch, that is the whole training set will run for 4 times. And now we're just setting the optimizer atom gradient to 0. That will save some memory. Here we just taking the mean rewards, and we're collecting all the all probability states, action, and rewards. We're just summing it up to get the total rewards. We're calculating the loss function from the previous surrogate loss function. We're just setting this gradient to 0. We just calculate the back propagation to compute the gradients, and we're applying our optimizer. And for freeing up some memory, we're deleting the loss. And by here, we are just getting the total rewards, and we're taking the mean rewards and we'll just run this train this code for 250 episode, and we are just printing at each 50 episode the average rewards, and we can see that the reward value is changing. uh, for first 50 episode is somehow increased, but somehow it is just getting negative and negative. That is, the training is going well, and it almost take 12 to 25 minutes to train the agent to 250 episodes. And if we upload the graph, then we can see that is over the progress of episode, the total reward is increasing. Here the blue ones means the reward at each episode, and the red one is giving our mean value of the moving average episode. There, here we can see the code, that is, we are taking the mean value of each episode to calculate the moving average reward. And if we want to render this training in gameplay form, then we have to render this code for physical visualization. And here we are just taking left and right random choice as frame 1 and 2, and we're taking some step functions. And here we can, if we run this code, then you can see that that was our trained agent. Now, previously, when it was in untrained form, it was just not performing well. But here you can see that it is very performing well, and whenever the total video is of 19 seconds. After finishing 19 seconds, we can see that it has indeed won the match for 20 times and lost for 2 times. So the train agent won the match for 20 times, and the policy approximation can be proved if we could train the hyperparameter, that was the epsilon, that was the beta, that was the risk control factor, and the training time was longer because we just took 250 episodes for training of 25 minutes. But if we could make it a bit longer, that will cost some computational memory and computational resources, but the performance would be a bit better. That's all my understanding about proximal policy optimization. Thank you.